let me just briefly review what we have discussed over the last, explain what deep sky objects are, what visual observation entails, and who should do it, what kind of skill set you need, and what a good approach for it would be. I also explained why I do visual observing as opposed to, let's say, imaging. And I also explained, we went in great detail about eye physiology, right? That was part one. Part two of the talk now, or previous session, part two of the talk, I went over how to assess visibility of deep sky objects, how to measure their brightness, and how to plan an observing session and kind of execute it, and where to find objects and things like that. This talk, we will go over deep sky observing, the actual process of observing. So you can see my outline here. It roughly says finding objects through star hopping, optimizing equipment, picking the right eyepiece, and then we'll talk about observing with lots of case studies. So that's the plan for today. And if there's enough interest for a fourth talk, then I'm going to talk about stories, like stories of meeting various observers. I've titled it Sources of Inspiration, inspiring, and split it into three categories: inspiring observers, very observations that I think are very cool, and my personal story, if you're interested in that. So, but this session is all going to be about observing, right? So, is this a good time to get started, Kirti?
Yeah, Akash, let's start.
Okay, cool. So let me get into star hopping. I didn't want to talk about star hopping because I didn't have a particularly refined technique, but I thought about it a little more, and I guess everyone wanted to hear how we star hop. But I realized that everyone has their own way of star hopping. So what I will present is my way of star hopping. So let me get into it. Like I said, everyone has their own way of finding objects. It doesn't even have to be star hopping. Star hopping is just one way to find objects. The other way would be to do push to, which is to use these things called digital setting circles, which are basically encoders, and you can push your telescope and it will tell you how to navigate your telescope to the object. And then there is a method called go to, which you punch in the object into your telescope, and your telescope, which is motorized, just takes you there. The problem is push to and go to don't work with great accuracy as we know them today. And so it feels like even though push to and go to make finding objects easier, you still have to learn, at least my opinion has been that you still have to learn star hopping first to know how to make sure you're on the right object, right? So push to and go to will not get you right on the target, especially if you're looking for something faint. And the other thing I want to say is all methods are respectable. I mean, whatever helps you find an object. There is a tendency amongst some people to look down upon anyone who doesn't star hop, right? Saying they're using automated methods. I don't know. I mean, once you've found a few objects by hand, I feel like the fun in finding objects gets less, and I feel like the fun shifts to actually observing and trying to discern the detail in the object. So I tend not to look down upon people who don't star hop. Someone has the audio such that it's causing a feedback loop. Could you mute yourself? I think now it's all right. So everyone, like I said, everyone has their own way of star hopping also. Some people like to use star charts. I like to use software. And everyone has different kinds of finder scopes, different kind of telescope mounts, and they have various ways of matching the star patterns that they see in the eyepiece to the star patterns that is in the star chart. Um, so, uh, like I said, my attitude is that I think finding objects, loses initially. That was all that we enjoyed, right? The joy of stumbling upon a faint fuzzy was everything. Now I think it's shifted more towards observing for me. And so my attitude is that dark sky time is precious, and whatever is the fastest within the object budget and is enjoyable, that's the right way to find objects. Whatever works for you is the best way to find objects. Um, so in this talk, I am going to present my version of star hopping, and it's definitely not the only way. And I hope that this will spur some discussion on the WhatsApp group. That I'm also going to learn from it, because I realize I'm not a very good star hopper. Many ideas that I put in this presentation only came to me in the last 2 years. Earlier, I used to go with more cumbersome ways of star hopping. Okay, so my method for finding bright objects is to do coarse alignment and search. Here's an example, the case study of Hercules globular cluster M13. I guess if you study a star chart, this is the object, by the way. So if you study a star chart and know your constellations well, so of course you should know your constellations well. That's the first thing in any sort of visual observing, because they are your landmarks in the sky. So this is the keystone of Hercules, the 4 stars that I've connected really badly. So if you look up at the sky, you should be able to recognize the keystone of Hercules. And I think this is the eastern side, or the western side, sorry. The side that rises first, I think, is this one. But you can always look it up in the map. And you just find these 2 naked eye stars and roughly estimate the position of the and just put your finder scope, whatever finding scope you have, preferably a 0 magnification scope. You put that there, like I've shown here. That's not the exact position of the globular, but you put it roughly where you think the object is. And then you move around a little bit back and forth, and you will stumble upon the globular. For bright objects, this works. Like I say, you just approximate it and use a wide field eyepiece, like whatever it gives you, like 6 to 7 millimeter exit pupil, the biggest eyepiece that you have. You just use that to search around and find the object. And you keep repeating this as needed until, if you get lost, until you find the object. This is kind of similar to the spiral search feature that some go-to telescopes have, right? You're just doing it manually, and not necessarily searching in an exact spiral. So this is simple for bright objects. For this, I recommend not using a finder scope. Somehow I've been very, but I mean, again, like I said, whatever works for you. For me, I find that finder scopes get in the way of this kind of rough positioning. So I recommend this thing called a reflex sight. This is a brand called Telrad, is very popular amongst reflex sights. This reflex sight is what it does is it projects. So you see this the window pane here, like the piece of glass. It projects a pattern. In Telrad's case, that pattern is a bullseye pattern. It projects a bullseye pattern on that glass that you can adjust, and you view the sky through that glass. So you see the bullseye as if it was marked on the sky, and that's how you center the object. There are other things that are I forget the word they use for this, but the 0 magnification finding tools. There are other things like red dot finder and just having a sight tube. My very first telescope just had a tube of metal that acted as the sight. So these things are I think reflex sight is the best of the 3 types that you have, followed by red dot finder, followed by sight tube. But whatever you have, this is for rough objects. Generally this kind of finding tends to work really well. Now, for fainter objects, I'm going to use as a case study this extremely faint object. I mean, it doesn't matter what object you pick, but as a case study, I'm just going to use this faint galaxy cluster. That's a sketch of this faint galaxy cluster called the Corona Borealis cluster, appropriate for the quarantine situation we are in. And Oh yeah. After I forgot to mention this. I guess that applies more to the previous case. After you center the exact field, you raise the power. You start with low power, and then you raise the power after you center the exact field. Anyway, so let's star hop to this as an example. So the way I star hop is I have two finding objects on my two finder scopes, if I may call it that, on my telescope. One is a Telrad, a reflex sight. The other is a 9x50 correct image finder scope. So I use both of them to actually find fainter objects. So this part I would do with a Telrad, right, or with a reflex sight or a sight tube. First of all, I would find the constellation of Corona Borealis, the northern crown. So those are the stars of the constellation. And this star is the brightest one, called Gemma or Alphecca. And I would find this star. And I would say, okay, it's here. So I would roughly put my reflex sight roughly in that area. So this is the rough star hop plan. Now, one thing I wanted to mention that is rather important here is I have put my software in alt-azimuth mode. So it is showing me the sky as I would view it for that time and location, right? So up in the chart actually means up in the sky. So if I may put it more clearly, this is not north. This is altitude up, right? So it's not in an equatorial orientation. Now, if you use a star chart, you have to orient it manually. So using software already takes that difficulty away from you. But if you want to use a star chart, remember that a star chart is designed to be held up while looking at the sky. So you orient it correctly for the location and time that you are looking at this object from. So I would roughly put my Telrad or whatever is my zero magnification scope over there. And I recommend that people get a correct image finder. It's not completely necessary, but it removes some of the difficulty of star hopping, because this one makes sure that the image is exactly the same as what you would see with your eye, in the sense that the field is not inverted or flipped. Now, if there are some finder scopes that come as called right angle finder scopes that have what is called a star diagonal, just a regular prism in this location. And what that does is it flips, it makes a mirror image in one side only. And that is extremely confusing. I strongly recommend that you don't get those star diagonal things, because you have to flip your star chart, and there is no way to do that unless you are using software. Now, if you're using software, SkyChart, also known as Cartesian, this software allows you to flip the sky map. So you could use that in principle, but it even makes movement also difficult. This finder scope, as I learned yesterday, has a different kind of prism that produces an erect image on both axes. So it does not flip the image. It's a little more expensive. I think I paid $100 for this. But if you don't want to use this, I would recommend that you get a finder scope that is straight through with no diagonal or mirror, right? No prism, basically. Then your field will be inverted, so you have to ask your software to invert it 180 degrees. And again, Cartesian, which is SkyChart, does that. So there's an option to rotate the map by 180 degrees. So set it to the right time, set it to the right location, invert by 180 degrees, and it's going to show you exactly what your straight through without any prism inverted image finder scope will produce. If you're using a correct image finder scope, you don't even, like what I've shown here, you don't need to make any changes. You just set the correct time and location, and it's going to produce the same map that you are seeing through the eyepiece. You don't need to rotate it. Eyepiece of this finder scope is what I mean. So So that will lift a lot of the heavy work of matching the star patterns because they're all oriented correctly, and that's very useful. So this is the field of my finder scope roughly. Okay, so over here is where the object is, and I from this I know that I should, if I put my gun sight or telrad in the right location, then I see that these two stars should be in this location, and I know that's the rough position of the corona borealis cluster in my telescope. In my finder scope. So here's a more zoomed out version of that. Notice these star patterns. So this is what we are going to use to star hop. So like in this case, this L-shaped pattern and this chain of stars here, they frame that object, right? So these are like landmarks in the sky. Now, depending on your finder scope and sky quality, you might not see the full star pattern. Then what do? You just estimate you keep this bright star at this location and just estimate where it should be, right? You guess roughly where the object is. But if you can see those patterns, then you know exactly what to center. You want to center this point, or maybe you want to center the pattern, so you can confirm that the pattern is correctly aligned in your main telescope. So then what do? This is an intermediate field eyepiece. So that's the field of view of the intermediate field eyepiece that I've drawn. This is a 40-minute field of view. The finder scope generally has like a 5-degree or something field of view, whereas the eyepiece will have a much smaller field of view. So you should keep that in mind. This is what you can expect to see in the eyepiece. So you should create these patterns of stars and rotate them in your head to match the eyepiece view. Hopefully you're not observing again with a star diagonal, because that really throws you off. If you have a Schmidt-Cassegrain with a star diagonal, see if you can do something better. But for most Newtonian telescopes, the field only gets rotated. It doesn't get mirrored. So whatever patterns you have, they will rotate around in some random orientation. So you have to match the eyepiece. So here are some example patterns that we discussed. We discussed two of them, the L shape and the chain of stars here. You could also use this pattern of 3 stars forming an obtuse angle. Now, and then you look in the eyepiece and you see if you can find these patterns and match them, so you know where the object is in the eyepiece. Because many of these objects, unless you know exactly where to look for, you're not going to see them. So that's these patterns help for that reason. Finally, I have a shortcut for this. There is a calculation that I came up with to rotate the eyepiece field to match, field to match what you expect to see in the eyepiece. This is mostly for Dobsonian telescopes only, or like alt-azimuth mounted telescopes. So you can use that. This is the software called K-Stars in which I've put this calculation. I also have a web version of it on a website. On my DSS query that I showed last time. So you can use this to figure out what orientation you will see in the eyepiece. So you see this L-shaped pattern of stars has become oriented like this. If you go between the previous slide and this slide, you'll see that it's rotated. So this software tells me exactly how it's oriented. If somebody is interested in making an independent tool for this, contact me. I'm happy to give you the calculation so you can find better ways of making it available to everyone. Otherwise, if you don't have the software, and that's fine, you can just rotate it in your head. But I prefer using software on the field. I know it takes more work because you have to keep a charger for your laptop and so on and so forth. But I feel like it takes away a lot of the work out of star hopping. The other thing you could do is you could use phone software. But generally, the phone screen is too small to be working with. So you can use the phone software to get the orientation that you have to rotate your star chart, and then use the star chart after that. That's also a good way of star hopping if you like star charts more. Now there are some people who will do all of this in their head, which is great. Just using star charts, but I prefer software. Yes, and the final star hopping happens in the eyepiece because you would probably center this pattern of stars, or given how approximate our positioning is going to be, this pattern of stars might be in some corner of the eyepiece. The idea is that you identify that that's the L shape, and then you say, okay, I have to move in the direction of the L, to get the cluster. So you do that, right? You move the telescope, and then you can find out exactly where it is. Um, so the images and star charts, of plotting these stars and their location of the object is kind of very important to give you an idea of exactly where you should be. Because if you don't center the object exactly, you won't even if you don't know where to look for the object, you won't be able to see it. These really faint objects. Again, after centering the exact field, you raise the power. That then so initially you start in an intermediate power, and then you go to your 2 millimeter exit pupil or whatever is the right magnification for the object. Okay, so I'll again pause here. Any questions on star hopping? Any comments?
Hi Akarsh, this is Kirti. So
Yeah,
I have a question. So
yeah,
when you are using the Telrad or the red dot finder, do you
yeah.
keep both your eyes open and look at the sky, or do you keep only one eye open and try to look through the Telrad finder?
That's a very good point. I like to keep both my eyes open. I think I find it very hard to see through that screen if I don't have both my eyes open. Although you can see, right? It's a transparent screen. Somehow it doesn't work very well for me. So I keep both my eyes open. It's only in the finder scope when I'm at a magnified finder scope, right? Like a 9 by 50 scope. That's when I close my non-observing eye.
Okay, yeah. I mean, yeah, same here. I also find it very easy to keep both the eyes open and kind of the first time it's a little bit difficult to do that, but once you get adjusted because of the parallax, and but once you get adjusted, I think it becomes really useful. The other question is, how do you so when you're doing this with high magnification in the through the eyepiece, the things keep moving in the sky. So how do you keep tracking them? So it's like sometimes if you don't know the orientation and if you try to move the telescope in some particular direction, you will lose the star. So
Yeah, yeah,
how
yeah.
do you keep tracking this?
So, I mean, in my case, the solution is that I have tracking. It's still possible to lose the object, and you have to re-find it, and it's a pain. But at least that means that you won't lose the object between running from your finder scope to your telescope eyepiece. But in the days when I did not have tracking, what I would do is I would know which way stars are drifting in the eyepiece, right? So I would know how to pull the eyepiece, push the telescope to bring the things that have drifted out of the field back into the field. So that's how I would do it. So even though I would have centered let's say I centered that L shape of stars, then depending on how that L shape of stars was drifting, I would actually see some other field. But because I know which way the stars are drifting, I'll be able to bring the L shape back. Does it make sense?
Yeah. So yeah, it makes sense. So I think one of the key things that you had told me when we were observing is that you always push the telescope towards the west direction. So you know where
Yeah, yeah,
west
that's
is, and
correct.
you just keep pushing it towards
You
the
push the
west.
telescope towards west. Yes, I think that helps more initially when you don't have a sense of how to push the telescope. But eventually, you gain enough, practice with the inverted field that it's just instinct. If you want stars from 5 o'clock, you know how to get stars back from 5 o'clock. So, but yeah, initially
Yeah.
you push the telescope west. That's another great trick.
Cool. Thank you. So there are some more questions on the chat.
Yeah.
What if the object has a bigger area like a nebula? These objects will have patterns inside them. Is there any software to recognize them accurately?
That's a very nice question. I would say no, there is no software. I know Cars kind of plots the outlines of nebulae, but Uh, First of all, the outline, I will explain this later again, but the outline of the nebula in H alpha and UH, or in H beta, UHC, H alpha, it will all be very different. So your best solution for that is to anyway get an image, you know, uh, assume that H alpha, H beta, and O3 are all aligned, get an image and use the image as a guide. Um, so I find sometimes DSS images are not enough because the nebulae will be so faint on the DSS image that you don't really see it. So you will have to go and find amateur astronomers who have taken these nebulae. Like there's somebody who has photographed all of the sharpless nebulae. So that's you could take their pictures as reference and then map the stars, or plate solve it in astrobin to find out what is the RA deck and try to orient it correctly. Um, but generally, what I do for nebulae is I find the part of it that is the brightest, and I find the stars nearest to that, and that's where I star hop to. I star hop to the brightest part of the nebula, and then you can move around and explore the nebula, whatever parts you can see.
Also, if the nebula has a cluster like, let's say, the Rosette Nebula or something like that,
Right.
I think it's easier
Yeah,
to.
it's much easier if the nebula has a cluster or some bright star or some reference point on it. But if you're looking at some very diffuse nebula that is in the Milky Way, so there are stars everywhere, then it becomes very hard to star hop. So you have to just find the perfect reference stars, have a big image have a good image as a reference, and find the various bright parts of the nebula. I think
Okay, okay.
nebulae are some of the most trickiest objects to observe.
Yeah, the supernova remnant in Taurus, which is very very faint but very very big. I think how do you observe that kind of thing?
Yeah, that's a very good question. I don't know if I've actually, I don't remember when I star hopped to Simi's 147. I want to say I've tried it two or three times and kind of seen it maybe once. Uh, yeah, things like that. Yeah, you have to find a image which marks the various reference stars that you know in your catalog, right? Some Henry Draper star, or like for Whale Nebula, it's very easy because we know 52 Cygni. So you just put 52 Cygni in the field, and then you know that the witch's broom is right there. Um, but for Simi's 147, you will have to like map out the stars that flank it and try to explore like part by part as if they are all very different objects, right? So,
Okay.
I mean, already for the Whale Nebula, we kind of do that. There's three fragments or four fragments, and you have to find all of them individually. For something like Simi's 147, it's just even harder. You have to find what are the brightest parts of the nebula that you can see and find it. I remember well, sometimes in when I was new to the US and I was observing with one of my mentors, John Tatarchuk. He used to find objects for me, and he'd find in his telescope things like Barnard's Loop, which Barnard's Loop is so big it spans almost half of Orion. But he'd find the brightest part and star hop. He knew how to star hop to it or how to move towards it from various other references. So and all you would see in a telescope is like a change from darkness to brightness, and I'll talk about that. So in some sense, some of these very diffuse nebulae, I think they take a lot of time to explore if you want to explore them fully.
Okay, okay. Thanks. There was another question.
Yeah.
So by Ravi too. I might have missed this, but is there any easy accessible software where I can plug in latitude and longitude and time and get a printable chart?
I think Cartosial is the best for that. I mean, it's designed to be producing printable charts. But again, if that's very hard to do because you might plan to observe this object at exactly this time, but when you actually go to the field, maybe there is fog at that moment and the fog clears out 1 hour later, then your chart is kind of useless. So uh, my attitude towards this is to rather take the laptop on the field or use a star chart on your phone to find the orientation and map it to your existing star charts. I just love to keep my laptop on the field because it's so much less work. I have to just carry a battery pack. Um, but I mean, in the initial observing days of mine, I never carried the laptop. I used to always work with star charts, and we just learned to. I used to use relative orientation, right? I used to form patterns of triangles, and it didn't matter to me how the chart was oriented. I think that's very taxing, and it's more prone to mistakes. It's better to know your chart's orientation correctly, which is what Amar Sharma used to do, and I never used to understand how he did it. But in hindsight, I think that's the best way to do it.
Hmm. Okay. So if you're finding an object, so is there a way to plug in the exact focal length of the eyepiece and telescope and get the exact field so that you know
Yes,
where you are? Okay.
yes, absolutely. Yeah, you mean the exact orientation, the exact size of the field, right?
Yes.
Yeah. So I think I put all of it in K stars. So you can actually, if you use K stars, which takes some patience because it crashes pretty frequently. But if you use K stars, there is a field of view symbol calculator where you plug in your telescope properties, you pick which eyepiece you are using, or you enter its apparent FOV, and it'll compute what is the size of the eyepiece circle, right? The field of view of the eyepiece,
Hmm.
and it'll draw it on the star chart, and then you can right click on any object and say give me an eyepiece view of this, and it'll rotate it for your Dobsonian. There are still
Okay.
some caveats, so if you want to use this, talk to me before you try it out, because there is this everyone's focuser has an offset. This is designed, all the calculations I've put into this is for obsession, which has a focuser on the right side that is parallel to the ground. Now, if the angle of the focuser is different, like it is on, for example, on my Orion 6 inch, the focuser is offset, and so I have to add an extra offset to this calculation. But yeah, it can be done. It's not fully implemented, but it can be done.
Okay, okay. Stellarium also has this eyepiece option, but I don't think it rotates the field of view
Yeah,
according
I think
to
very
the.
few software rotate it. They can render an eyepiece field, but they don't rotate it correctly for your telescope. And that's the part I've been I worked on basically to rotate it exactly. So you don't have to do any thinking at all. You can just rely on software to see exactly what your finder scope object should look, finder scope view should look like, and what your telescope view should look like.
Cool, cool.
I
Um,
have a question.
Yes.
Yeah, speaking about focus or offsets, is it recommended to do this? Because
Uh,
certain telescopes, take for example GSO or Skywatcher or Zoom in or all these,
yes.
they
Yes.
some people actually recommend changing the position of your focuser and turning it. Yeah, so should I do this? Would
I
this help me?
I think I think the answer to that is on small dobs. Having a focuser that is tilted helps a lot because you're usually bending down. On large dobs, it is the most horrible thing you can have. I never understand why some big telescope makers actually offset the focuser.
I see.
Because then you have to bend over your ladder and see at a different angle. But for small dobs, it makes sense. I don't think it makes sense for large dobs. Large dobs, I think the right way to look at the focuser is it on the right side or is it on the left side, which depends. Your preference might depend on whether you're right-handed or left-handed. So, but yeah,
Okay.
I think for small dobs, it's okay.
Okay. Okay. Thank you.
Okay,
I have a
so
okay.
I have I have a
yeah,
question. Yeah. So more in observation, right? So what is happening is I normally use star charts. So what's if I use the finder scope, right? So the kind of view I get in terms of the number of stars and all, I get lost there. So what I did is that normally, I think one of the star chart was giving a stencil. So a stencil for let's say 5 degrees, right? That's what will be the normally the field of view for a
ah,
finder scope, right?
yeah,
So using that
yeah,
stencil, I was trying to star hop, but the number of
uh-huh.
stars I see in the finder scope is far more than what I can see in the star chart
Star
itself.
chart, yes,
So
that's right.
then I really got lost. So the only way that was helping me was initially to position it, looking at some geometry and positioning it using
Yes,
Tele, and
you're
and
right.
then yeah, and then figuring out basically, using the low power eyepiece and using the telescope itself. But then I don't think this is a proper way, right? We should be able to
Oh,
further zoom it
okay.
using the finder scope.
Right. So the thing is, uh, this is a problem I have with K stars also. Is it's very hard to match the stars, the notion of the size of the star, right, to correspond to its brightness. It's very hard to match that across your finder scope, across your telescope, and your star chart. So you still have to make geometric patterns by grouping the brightest stars in your star chart and grouping the brightest stars in the finder scope to match them. I think even for me earlier, I used to shy away from the finder scope because I thought it was more work to deal with this intermediate field of view. But I realized for like really faint objects, there is no way that you can um, avoid the finder scope. I think for bright objects, it's okay to do what you just said. You will find them because you don't need to be exactly positioned on it. Chances are you're going to view it, and chances are that they will show up if you are at a wide field eyepiece. You'll at least be able to see the object. So some of these faint objects that we eventually want to observe, they are not even visible at the low magnification. Like we said in the previous talk, there is a magnification which allows you to see the object. And so for those things, you need very precise positioning, and that's where really the finder scope comes in. I mean, ultimately, it is whatever works for you. There is no right or wrong way to do star hopping. But if you want to make full use of your finder scope, then you still have to map patterns. Only thing is with all of these software aids, you have to rotate them in your head. But you still have to map which are the bright stars in the software to the bright stars in the finder to create patterns and find ways to confirm that you're doing this correctly, because it's very easy to go wrong in this. And I think the only way to get better at it is to practice and keep trying.
Yeah, okay. Yeah, see, another one last thing, another thing which is troubling me is like that the constant, from the eyepiece to the star chart, eyepiece to the star chart, because many times, we will not be having things in mind. You look, okay, I need to look for this pattern. By the time you go to the eyepiece, do some changes, you would have forgotten what kind of pattern it
Yeah,
is. Again, you
beautiful.
go back. So this is troubling me, and what happens is after some time I get tired. Right. So
Yes,
I don't
I
think
mean,
there
I
is a
have
way for this, but I think we should, I don't know what to do.
I've been thinking about this a little more, and I thought of maybe there is a way to mount an tablet like a iPad or whatever on the telescope, and that way you don't have to do this. For example, the previous owner of my telescope, John, he had he he had this way of keeping. He had this special setup to place his uranometria or star chart right next to the finder scope. So he set up the finder scope such that he can immediately refer to the star chart. So I agree. I think the faster you can close that gap, the more you can close that gap, it's the better. But uh, the other thing that helps is I keep describing my patterns to myself as I walk from one place to other. I'll keep saying, okay, right angle triangle with bright star on the angle vertex or whatever. So I keep saying that so that I don't forget what the pattern is while I go to the eyepiece. And as you get used to seeing more constellations, you'll also have names for bigger patterns. Like you might see, okay, this looks like the Southern Cross, so you keep say cross pattern, and then you go there, and that's how you can make a mnemonic to remember it. Like map it to a known constellation, right? So yeah, star hopping is hard.
Yeah, but it's a lot of fun. So just a small input. See, I don't know if anybody has gone through the book called Astronomy Hacks. So it is a wonderful book which is giving a lot of, what do you call tips? Like, as you said, right? We print a star chart, and using that lady was using a magnet to basically stick onto the tube itself. If it's a magnetic, if it's a metal tube, right? She just sticks it. So we don't need to move anywhere. We can just see the star chart. So
That's really cool.
yeah,
I
Astronomy
see.
Hacks is a very nice book, giving a lot of tips. So I think it's available in India only because I bought it very cheap here in India. So
Okay.
it's that. Yeah. So
Yeah, I haven't
Yeah.
heard about it. But
Yeah.
many people have come up with very great ways of making their job easier. And I must say that I have not thought of anything. I mean, my solution nowadays is to try to get away from star hopping as quickly as possible.
Yeah.
So,
It is just not star hopping. She will also tell how to observe, like that if you see a faint galaxy, right? How to see the patterns in that, how to train your eye. It's a nice book, so I would
cool. That
recommend.
kind of book is very useful. So I haven't looked at this, so I will look at it.
Yeah.
Thank
Okay.
you
I'll
for that
put the
reference.
yeah. All right. Thank you. I'm done.
Agar, just one last question. So, how
Yes,
good are these push to applications, mobile applications for finding the objects?
I am sorry to say that they are very horrible. The reason is okay. So for bright objects like big open clusters, Messier objects, no problem. I think you can use it. They will help you. But for anything fainter where you need exact positioning, they are horrible. And the reason is that um, these these things are not designed for the kind of precision we want in astronomy, which is sub degrees. Like we are talking about tens of arc minutes and so on and so forth. And the biggest variable in all of these is the magnetic compass of the phone, right? The magnetometer. You might have seen Harshad's app Sky always complain about strange magnetic fields. The problem is whenever you have a telescope tube or something metallic nearby, it can distort the Earth's magnetic field and kind of overpower it. And so it's very hard to get the absolute sense of where north is in a smartphone. And the only way the smartphone has a sense of where north is the magnetic compass. Much more reliable is to actually use encoders and have like 2-star alignment, 3-star alignment, these kinds of systems. They are much more reliable. Still, for extremely faint objects, I find that every visual observer, no matter whether they have the best go-to, best push-to, best encoders, they still have to do the last bit in star hopping. This is why I think star hopping is basic, even if you and go-to and push-to are only helpful for advanced amateurs.
Okay, thanks, Akash.
Okay, that was a very long discussion on star hopping, but I realized that it was one of the favorite topics that everyone wanted to talk about. So I'm sorry if we won't finish everything that I have planned for today, but I'd rather get star hopping through because of popular interest. To summarize what I said about star hopping, I just want to say try to use software to get rid of the rotation and inversion and so on. But ultimately, you still have to learn to match star patterns to star patterns. And the more you practice it, the better you get at it. It's very easy to go wrong. You'll have to find ways to make sure that your patterns are correct. And eventually you'll get the hang of it, and then I'm told that master observer Alvin Huey can star hop to an object before even someone can punch it into their go-to. So I mean, this is the extreme where you get really good at it. You can be extremely fast at it. I'm not yet there, so I'm still a novice star hopper. But yeah, please try it out and try to use software. Is my advice is try to use software to as much as possible offload the work of your brain. It also makes the chance of error less. Okay, so that's the summary of star hopping. Let's go to optimizing equipment and talking about tips on how to actually observe faint objects. Now, many of you have asked me about city sky observing. Observing a bright object in the city sky is exactly like observing a faint object in a really dark sky. Everything becomes much more harder. So I think if you are observing deep sky objects in the city sky, you are basically observing faint objects. So many of these techniques will apply to you when observing from the city. But yeah, let me get into optimizing equipment. So if you want to see really faint objects, you have to optimize every part of the instrument train. And there are multiple parts to this instrument train, right? There's the telescope, there's the eyepiece, there's your eye, and there's the brain. Okay, we've already talked a great detail about how to optimize the eye's performance, right? Like dark adaptation and averted vision. But and we have talked a little bit about the brain, saying we have to allow for the 6 to 10 second exposure. But we'll talk a little more about the other parts of this. So first of all, how do you make your telescope better? The first thing is make sure that your secondary is collimated. Some of these are sufficiently specific topics that in fact I haven't spent enough time doing them, implementing them correctly. Like I haven't checked my secondary collimation. I try to. Some people recommend that you center spot your secondary so that it becomes better. But sometimes it's easy to forget that one always collimates the primary mirror correctly, but one forgets the secondary collimation because it needs to be done much less frequently. But it's good to check every now and then that the secondary is square with the focuser, right? That's also important. Good collimation helps because it makes the point spread a little lower, so it concentrates the light a little more. Laser collimators make collimation much easier, but sometimes the problem is that the laser collimator itself is not collimated, right? If it's especially if it's mass manufactured and nobody has checked it for tolerance. So people recommend that you get there was this exceptional instrument maker named Howie Glatter. Unfortunately, he's no more. He made this laser collimator that he would test by dropping and such that, no matter what you do to it, it remains collimated. That kind of good design is in a collimator that you can trust is helpful. If you don't want to spend money on a collimator that you can trust, I think it's much better to work with Cheshire eyepieces and side tubes, which I don't know much about, but you can learn. There's a lot of literature on it on the internet on how to use Cheshire eyepieces and so on. So good collimation helps. Other thing is collimate where you observe, even if it means neck wringing while collimating. And the reason for this is tube flexure. Any telescope will sag a little bit as you change its altitude. So try to collimate at like 60 degrees altitude, which is where you should spend most of your time observing, right? So not horizontal, because the collimation for a horizontal tube will be different from the collimation for a 45 degree, 60 degree altitude tube, right? So collimate where at the typical altitudes that you're going to be observing at. Then of course you should have a clean mirror with proper coatings. All of this will help prevent light loss. But it's also important to prevent tube currents, which is the turbulence of air within your tube as your mirror cools down to the ambient temperature. So cooling fans are helpful to suck air and prevent the tube currents from ruining your view. Again, if you have too much air turbulence, that again spreads the light and causes problems. So you might not be able to see things very clearly. So all of this helps. And the other important thing is contrast is everything, like we've been discussing. So baffling telescopes is very good. Actually, Mel Bartels has a lot of information of baffling that I haven't explored yet. So that's a good place to look. But basic baffling is light shrouds. I'll show a picture of what that is. And light shields. These are ways to prevent stray light from getting into your telescope tube. And these improve contrast. Refracting telescopes have excellent contrast because they have these internal baffles that prevent stray light from bouncing around inside them. And I don't know if anyone has experimented with those for reflectors. I think it might be a very good idea to try. And these light shielding and shrouding are more important in urban skies because you'll have stray light coming from all around. So unless you block these light sources efficiently, your contrast is not going to be good. And in terms of eyepieces, different eyepieces designs have different amount of contrast. The general rule of thumb is that every glass to air interface, like whenever light goes from air to glass or glass to, I think air to glass, about 4% of the light reflects unless the surface is coated with a special coating. So one, make sure that all your eyepiece elements are coated correctly. And there can't be defects like air bubbles and things in the glass because those will again scatter light and cause light to spread around and lower your contrast. So high quality optics along with the anti-reflective coatings are what make an eyepiece have very good contrast. And also lowering the number of elements helps. So instead of going for these high field of view eyepieces, it might actually be better to go for the simpler eyepiece design like orthoscopic. Orthoscopic eyepieces are very popular for this reason because they only have, I think, 3 or 4 elements, and they give a decent field of view. And you can, if you get a multi-coated orthoscopic, that's a very good eyepiece to keep. But amongst the more wider field of view eyepieces, these are some of the eyepieces that are, noted by observers for their contrast. Teleview's Delos series, Ethos series, and the Pentax XW series, and there's one more called Baader Morpheus. I'm told that that's very good and it's slightly cheaper. But the cheapest good quality eyepieces you can get are generally orthoscopics if you don't mind the smaller field of view. Okay, so this is what a light, the one on the left is what we call a light shroud. It's basically like a sock wrapper around the telescope. The one on the right is what we call a light shield. You can see that it is placed against the focuser, opposite, so it prevents stray light from hitting the back of the eyepiece and getting into your eyepiece and ruining contrast. I think a light shield will be very helpful, especially for city observing.
Akash, I have a question here.
Yeah.
Regarding the light shield. So I have a light shield from Farpoint.
Okay.
The only difference here is the AstroZaps one. It has I think the Velcro, the thing that it will sit on the outer circumference of your OTA, right? But the one that I have, it sits in the spider veins, so it makes use of 3 spider veins.
Oh, that doesn't sound very good.
So yeah, that's what. So I have not used it yet. So I just wanted to know if that would affect the collimation, etc. Because if I am going to be placing the light shield that way, then it would probably affect the secondary mirror.
That's a very good point. I never thought about that. Yeah, that's. I don't know how much it will affect you. That's something you'll have to try. To be honest, I don't use a light shield much myself. Like I said, some of these improvements I haven't done them myself. So this is not entirely practice what you preach kind of thing. So I don't know very much about light shields. I remember that my telescope's previous owner, he had a homemade light shield and it kind of fell apart. I still carry it around, but I never use it. He would use it whenever he was getting very serious. But I think this kind of light shield that fits outside the telescope is a good idea. I haven't tried it yet. That's something I should try. But light shroud, I always religiously put it on.
Okay.
So I mean, what I have found is if you try to keep anything on the spider veins, the veins may bend. So you have to be very careful as to not put any weight on the spider veins.
Right.
The easy way to do this light shield is to get a kg cardboard sheet, black colored kg cardboard sheet, and just wrap around the whole OTA. So I do that for the small SET telescope, Navin's 6-inch SET. So the SETs actually, yeah, I mean, they at least the Newtonians have a little bit of gap from the top of the tube to the focuser, but in an SET, it's like you have the glass element which is at the very top.
Yeah,
so,
correct.
So you definitely need that kind of light shield which is all around, and yeah, it can extend up to, let's say, 1 feet or something like that. And it's very easy to do with the cardboard sheet, and you can just stick it with a tape or something.
I guess the hardest part is you want it to be removable, right? That's why I guess people use Velcros, and it should hold its form when you remove it and put it back many times. That's the biggest challenge, but one-time use is also fine. The problem is it should not get destroyed in transport.
Right. So you need not actually put the tape. So if you just what I was trying to say is you just wrap the sheet around the tube and you tape the sheet, not the tube, and it just keeps. So if you wrap it tightly, it just stays there.
I see what you're saying. It keeps its form. Okay.
Yeah.
Smart. So I have sung praises of tracking. I will continue to sing praises of tracking. I know it's very hard, but it's still optional. I would say you can do a good job without tracking. The obvious advantages of tracking is you're less likely to lose the object at high power, and there is less frustration of keeping on moving the telescope to track the object. But the less obvious and more important advantage of tracking, as we said, is that the object stays in the same place. So your eyes can spend those 6 to 10 seconds of integration time to actually detect the light. So the eye-brain system spends less processing to follow the object as it moves in the field. Some visual observers anecdotally say that this is equivalent to buying about 25% larger aperture if you have tracking. So that's what made me eventually buy a tracking platform. And the tracking need not be of astrophotographic quality. You can just have equatorial platform or alt-as friction drive. It doesn't have to be very sophisticated. It is possible to build your own equatorial platform. I'm just not mechanically talented, so I ended up buying one. This is a crossbow equatorial platform. It's for 30 degrees latitude, but now I use it at 38 degrees latitude. These things for visual, it doesn't matter. The polar alignment that I do is I just say, okay, that's the rough direction of north, and I just set it up. It doesn't have to be very high quality tracking, but if it keeps the object roughly in the same part of your eyepiece, it's enough. So all sorts of kind of jugaad tracking methods will work very well.
I have a question here regarding equatorial platforms. So recently I tried making one, but again, just like you, I am not mechanically talented, so I ended up wasting the money, and it didn't work out at all in the end. But so now the question here is how much would it cost for to buy an equatorial platform in India, if you know anything about this?
I don't know. I would wonder if somebody like Kuldeep Vora can produce these. For Indian latitudes, in fact, the platform design is very different from what we have to do for higher latitudes like 30 degrees. In especially for South India in Bangalore, you can just shift the entire telescope up 13 degrees. We can't do that here. We can't shift it 38 degrees. It will fall. Right. So there has to be that these platforms are designed to cut an arc of a circle and so on and so forth. I suspect that the designs for platforms that you need at low latitudes are simpler. For all it might just suffice to
add a wedge.
I really don't know much about it, and
okay.
It would be nice if someone would make this in India.
Yes. Okay.
I wonder if it's easier to build a friction drive than building a platform. I guess it depends on the size of your telescope. The problem with this friction drives is you have to calculate in alt-as, to drive the telescope in alt-as, you have to calculate how you should drive the two motors. At least in the US, I can quote prices. This might be one of the cheaper equatorial platforms you can buy, and it retails for about $1,000.
Okay.
Whereas the friction drive retails for much higher. It retails for $2,000, $3,000. But I think you can build this for much less if you are willing to work with wood and so on and so forth.
Okay. Yeah. All right. That was my question.
Okay. So picking the right eyepiece, we have talked about this before, but there's a question: what power should I use for a DSO? And like I said, there is some theory. There are some attempts at a theory, but we are more interested in these rules of thumb. The rule of thumb is that the detail of interest should subtend about 1 to 2 degrees at the eye. For most NGC objects, it's very hard to generalize something across all of NGC. There are different sizes of objects. But for most objects, you say you typically start at 10x per inch of aperture. So if your telescope is 8 inch, you start at 80x. This is equivalent to the 2 millimeter exit pupil rule, if I remember correctly. And then you bump up and down the aperture, down the magnification to try what works best. There's no one calculation that will tell you which eyepiece to use. Every experienced observer that I know always changes the eyepiece to see what can they see something different and so on and so forth. So you will see different details at different powers and all of that. That's why it's useful to have a wide range of eyepieces. I avoid Barlow lenses because, again, Barlow lenses are more elements. They might not be coated as well, and so they can reduce your contrast. So I tend to actually have a collection of eyepieces that I've built over the years. I didn't splurge all of this money once and for all, but I built it over the years. And if you are worried about the price, I would suggest going for simple eyepieces that are well coated, like plausibles and orthoscopics. In fact, when the expert visual observers get very serious, they probably put in an orthoscopic or a monocentric or a plausible eyepiece just because it has fewer elements. So the important thing is to have high optical quality and good coatings. How fancy your eyepiece is doesn't matter beyond that. And notice that I've this is not intentional, but it has become that way by experience, that my eyepieces are spaced roughly equally in power, which means that as you get higher and higher in size, as you get to higher and higher magnifications, the focal length spacing reduces, right? Like, so for example, I'm going from 10 millimeter to 7 millimeter to 6 millimeter to 4.5 millimeter. That's because it goes like 1/4 focal length of eyepiece. Those magnifications are spaced roughly equally apart. So I have different things to try back and forth. And I've underlined 10 millimeter because that's, for my telescope, that's roughly where the 2.5 millimeter exit pupil is, or 2 millimeter exit pupil is roughly there. Okay. So like I said, I would rather focus when making, earlier I used to think that, large apparent field of view like Nagler eyepieces or, all of these ultra wide was the way to go, the 82 degrees, 78 degrees. But more and more I realized that contrast is the key parameter, not so much A of OV, because that's what allows you to see fainter things. And my personal favorites are Teleview Delos and Pentax XW. And somebody who has done a lot of research on eyepieces, A-beat them extensively, recommends this thing called Baader Morpheus. It's cheaper than Delos, and I think even Pentax XW. But if you want value for money, then multi-coated orthoscopics. There used to be this company in the US selling these multi-coated orthoscopics made in Japan, but they had to close down. Now, I would be very curious if somebody knows about good Abe orthos that are, multi-coated, that are cheap. The only one that I know of right now is definitely not cheap because it comes from Takahashi. But they are, again, very good eyepieces. I think of all the eyepieces listed here, the Takahashi is actually the cheapest because it's a simple and old design. But like I said, what matters is not how fancy the eyepiece is, but how well coated it is and how good the optical quality is, because that's what determines your contrast. And like I said, avoid Barlows, avoid Paracore. Some people like Paracore, and I still don't know why, but I avoid them simply because I don't want to lose light. So here's a display of my favorite eyepieces. Yes, there seems like there's a question. Is there a question? Okay, I guess.
Yeah, Akash, I think you're talking about the TMB design. Are you talking about the TMB design? Which got,
I am not.
So
TMB, TMB is monocentric, right?
it's
I don't know what TMB stands for, but
ortho. So yeah, it was quite popular for planetary. That company shut down, but there are a lot of Chinese knockovers which are available on AliExpress. They're still branded TMB, but yeah.
I see. Interesting. Again, like I said, these simple designs, plausible, monocentric, and Abe orthos, these are tried and tested designs that are really good. And what matters is the quality of the lens making and the quality of the coatings. So if you can ascertain that whatever company is producing that is able to do that. Generally, I've heard that Japan has the best coating technology.
Yeah, I
So
can.
generally, if you can figure out if it's of good quality, then it doesn't matter what the price tag is. As long as it's of good quality, it's a
Yeah,
good eyepiece. That's it.
I happen to have an orthoscopic eyepiece from Japan.
Uh-huh.
So it is called the brand. It is called KK. If you have heard of it, Kokusai Koki.
Haven't heard of it.
Okay, so this is a 5
Okay.
volcano top eyepiece. So it is not in manufacturing anymore. So it is a very old eyepiece.
See, this is the problem I have. Almost every ortho that I know is out of manufacturing. Like the Zeiss
Right,
orthos are very precious; they are out of manufacturing. The TMP
right.
monocentrics are out of manufacturing. There's one more company's name that is often thrown around. Something from B, I can't remember.
Oh, then I can
But
direct you to an orthoscopic set of eyepieces which are still under manufacturing and which are really good.
that would be very helpful. Thank you. I think everyone should know that information because I mean I think uh, Delos is great and I really love Delos, but it's expensive. So
Okay.
if you can get the same contrast for a third of the price, I would love to know how to do it.
Oh, so I would suggest also, just like you mentioned, University HD orthos here.
Yes,
I think the manufacturer is the same for a couple of brands.
yes, I've heard so.
Yes.
So
So
if
now,
you can trace those brands, that will be amazing.
right now, you have a series from Baader called Baader Classic Orthos. They are called BCOs.
I see.
So you have, I think, 4 or 5 eyepieces that Baader makes,
Uh-huh.
and they are regarded as good as University Optics. Some claim that University Optics shut down, and then Baader Classic Orthos came out. They are actually the one and the same eyepiece. There is no difference.
I see. Interesting. So thanks for that tip.
Yes,
That I think is very useful to everyone on this call because any cheap good ortho that's relied that is trustworthy
right.
is. I also point my friend who is very good at eyepieces to check it out and let me know what he thinks and. I usually trust his opinion, and he so far said that the Bader Morpheus is very good.
Okay. And for about $250 you can have 5 eyepieces. So that is quite it retails at, I think, $80 per eyepiece. But if you buy
That is
the set,
amazing.
it's a quad turret. It's called a quad turret. So if you buy 4 eyepieces, you get it for $250.
Wow, that is very good because
Yeah,
I
and
bought the University Optics HD orthoscopic for something like $90, and I
right.
use it for all the wide field, really faint diffuse nebulae.
Oh,
That's
okay.
what I pop in. So
And what is the field of view of your university optics?
it's a 26 millimeter, but I think the orthoscopics produce like 55 degrees apparent field of view. So that's what it's the standard of the orthoscopic.
Okay. With this one, you get 52 degrees with the BCO. And
I
the
see.
one I have, the KK that I have, it is 43 degrees. So at 5 and 43 degrees, I do get great views of Jupiter and Saturn, but they run out of the field of view very
They
quickly.
are not very hard. Okay, yeah,
Yes,
that's true.
yes,
See, that's where tracking again helps.
yes,
So it also allows you to use cheaper orthoscopics. That's another advantage of tracking.
yes. And somehow, ever since I have used the 5 I really love orthos, and I feel like I want to switch to orthos altogether.
Me too. So
Yes,
anyway, so orthoscopics. So that's about eyepieces. So we have talked about the telescope side of things, the eyepiece side of things, and now we'll talk about, and we have talked about the eye and the brain. There we'll talk a little more about the eye and the brain. Um, so this is so observation is like I said, eye plus brain and not just eyes. So you want to focus the brain's processing efforts. You want to not have other things to worry about other than whether you can see this faint object because that's what you want your brain to be doing full time. So, and spending greater than a minute about per object is essential. Long lines at a telescope at a star party, there are a lot of fun. Star parties are nice, but they don't give you a real feel for what observing is like. When you spend those 1 minute or 2 minutes at the eyepiece, that's when you start really seeing details. Um, so, uh, And whenever I'm seeing like really faint objects, I use this hood. This is actually a very nicely designed observing hood by one of my friends, Dragon. He unfortunately doesn't sell this anymore, um, but you can just use a towel, right? The big problem of putting a hood on is that your eyepiece will start to fog when you breathe out, especially in humid environments. And one of my mentors, John Tatarchuk, he had actually uh, used a fish tank air system to push air on top of the eyepiece so that the dew would not form. Nowadays, my solution is that I avoid observing when it dews, but if you cannot avoid doing it, then you might want to try to come up with some ingenious mechanism like that so that you can use both your hood and not fog the eyepiece. The other thing that I sometimes do is hold my breath, but again, that will deprive your brain of oxygen. That's not good for your observing either. So using a hood is a bit of a challenge, but it really helps. Then this again, we have said creating movement helps. This is a very well-known thing. Tapping the telescope, moving it around to see if something happens. And this is a trick that I learned from Jimmy Lowry that says you rock the focus back and forth. It creates movement, so your eyes are going to catch it, but it doesn't move the object around, so you still get that the exposure effect. So that trick works sometimes, especially when you're looking at faint but high surface brightness. By that I mean tiny galaxies of 15th, 16th magnitude. It really helps. Sometimes taking a break helps. Again, gives your brain some rest, gives your eyes some rest. Normal breathing helps. People try to say you hyperventilate. I'm told that this works at higher altitudes, but it doesn't have much effect at normal altitudes. But holding your breath is still a bad idea, I think. You have to be well fed and well hydrated. Those things help. And I already said try different eyepieces. So observing is a lot of there's a lot of stuff that goes into observing, like these things. So I'm now going to go to a few case studies on various things I've talked about. These are sketches I made in 2009 with the 17.5 inch. This is from Coorg in Karnataka. On the left is I think some of these are not sketched at the eyepiece. I came back home and tried to sketch whatever I remembered. I had a photograph of this, which is bad, but I tried to match whatever I remembered only and whatever I saw. But here's what I remember made the difference that magnification made. When I started out in the field, people had told me you should use low power to concentrate the light of the objects. That's not entirely true, right? Magnification does help. And so here's a classic example. I was not able to see the spiral arms of this faint M74 at lower power. I think that power on the left is about 100x. No, maybe a little less. I don't remember what's the focal length of the 17.5 inch. On the right, I have put 2x more power. Back then, I used to use a Barlow, and suddenly you see I'm able to separate the spiral arms and things like that. So power can make a huge difference. Here's another example of changing power. This is a more obscure thing. Hickson compact group number 1. It's a compact group of galaxies. I've seen two features here in this log. One is this clump of two galaxies, and here's the other single galaxy that is within the range of my 18 inch. This is from my 18 inch. And you see at a lower power, this is about 200x in my telescope, the first one. I can see the clump easily, but I can't resolve the two galaxies. And I find the second galaxy here a little harder to observe. So you have to rotate this thing a little bit towards the right. The image slightly rotate to the right to match the log. This galaxy is harder. But now when I put more power, this galaxy becomes easier and this clump becomes harder. But the advantage is I'm able to resolve the clump into two galaxies. Like I've said here, I've sensed clear resolution for a few flashes, right? So different power will show you different features, will resolve different parts of the image, and one should always keep trying different powers when observing. This was a mistake that I made in my early observing. That's why I'm emphasizing it so much. The other big question, especially as a beginner, is how do you know what you're seeing? Whether you're seeing the real thing or you're just mistaking something else, and you're not like noise in the eye, if I may call it. And especially because for these faint objects, if you don't know what to look for, you won't see things. So you always carry an image to the field. So how do we know that we are seeing correctly? And I think it's learned with experience. You learn to trust your eyes and your observing skills with time as you get more and more faith in them and know what is possible and what is not possible, right? Some techniques, if you're a skeptic, is you keep an unknown aspect of the image that you have not noticed, and when you go to the field, the eyepiece field, you observe this, and then you come back and check against the image. That's one way to do it. The other thing that happens is if you have multiple observers, sometimes multiple observers will describe word to word something that they saw that doesn't match the field. That tells me that clearly that doesn't match the expectations from the image rather, and that tells me clearly that they are both seeing it. The other way to check is you try to center a faint feature and check the star field and measure, like in your eyes, everything, and check against the image to see if you're seeing it correctly. And you get to know your threshold. If there's a noise in the eye, or like I don't know, I sometimes hallucinate things. Good observers don't. I still sometimes hallucinate things, and so I keep checking myself. But I know that a lot of even professional astronomers tend to believe that visual observers are just making things up and there's no way they can see all of these faint things. I completely disagree. You can have 3 or 4 observers on the same field, and when they all look at something, they all agree, generally. They might see different parts slightly differently, but overall there is consensus. And that tells me that observing is really a science. And you see the amount of effort that we have put into making this work with all of these optimizations. When somebody blindly tells you that there's no way you can see. I heard a professional astronomer say, there's no way you can see anything fainter than the Andromeda galaxy with the naked eye. That's completely wrong. People have seen M81 and 82, and I have no reason to doubt. Sorry, not 82, M81, and I have no reason to doubt that they have done it, because you now have seen all of the effort it takes. So it's good to be skeptical, but it's not good to shun the entire experience, right? These observations generally corroborate. Here's a case study of checking what you're seeing. This is an extremely faint object that I tried multiple times called Maffei 2. It's a faint galaxy that has been obscured by the Milky Way dust. Here where I have said I remembered the position kind of wrong, and I pinpointed the glow from reference stars, and then I went back to the DSS image, and I had found out that I had pinpointed the exact location of the object. So that's how I was able to tell that I had seen this faint object. Also, the other thing that can confuse you sometimes is that there are faint asterisms of stars that you can sometimes mistake for the glow from a galaxy, right? So I had to distinguish it from the glow of the few stars in the field. So I tried to resolve those stars and hold those stars in the field to confirm that what I was seeing was not the asterism, but the galaxy itself. So this takes some time and experience, and this is where I highly recommend, I've said this before, observing with people who are more experienced than you really helps, because that's when you realize, when two people really agree on it, that's when you learn what are the limits of the visibility. So I recommend observing with more experienced people. We have already said this again. Things objects at the limit of visibility will pop in and out. They don't always stay in your view. They brighten, they darken as your eye tries to make sense of this faint field. And I've listed a bunch of speculative reasons, but this is definitely everyone's experience. I showed you a plot earlier from Roger Clark's article in Sky and Telescope. This is where you come up with things like, if you think you saw it 3 times, you lost the object. This is a common rule that that many visual observers use. If you had 3 good pops of an object, then that's like the very low probability of folding. You log it. And there's also the question of how percentage of time you can hold the object. That's usually some people like to write them down on their logs, and I try to do it approximately. Okay, I'll pause at this point and ask if there's any questions, because I feel like I've talked for a long time.
Yes, I have a question.
Yes.
Is there some better method for the terminology used while you are logging something? Supposing, especially for objects which you are uncertain of. Is there a vocabulary of observing log that you can use, so that every time you make another observation, you're more sure of what you've seen?
I am not a very systematic logger.
Okay.
But the one terminology I tend to use is percentage holding, like how much I can hold an object. And I generally rank on a DSS image which objects I saw were brighter, and I'll rank them in the order of brightness.
Okay.
But you should look at Steve Gottlieb's observing notes. His logs, I mean, he paints a picture in words. If you can log like Steve Gottlieb, that'll be great. So he's the person to look at for ideas on how to organize logs.
All right, thank you.
So I think we are at the 1.5 hour point. How do people feel about going further, or should I defer this to a different time? I've only gotten a half as far as I thought I should get. So.
Akarsh, we have about half an hour more. You can continue for half an hour if you think you can finish the particular topic. Or
I think I can finish this topic. Okay. But I also at the same time want to ensure that everyone's questions are discussed, right? I might not know all the answers, but it's good to the purpose of this. The other purpose is to stimulate discussion. So okay, so let me.
There is one question from Leela ma'am. Could you explain further details on eyepiece uses? They look very different from normal ones. So I'm not sure. Leela ma'am, if you are there, you can elaborate on that question.
Yeah, I also did not understand the question.
Yeah, and there's another question on eyepiece dust caps, if there are any available in India.
Yeah, I would not know, but that's a good question to ask. If anyone knows, please chip in.
I guess few of the eyepiece dust caps can be sourced from AliExpress. I don't see any particular Indian manufacturer or Indian dealer they produce. But yeah, most of the time I do source from AliExpress. Yeah, that's all.
I see. Here in the US, I usually go to a website called scopestuff.com for those things.
Okay.
In case somebody is traveling. Yes, sorry.
No. Can you hear me now, Akash?
Yes, I can hear you, ma'am.
No. See, suddenly I heard of this new term, ortho something eyepieces. I never heard of it before. And you had displayed a whole lot of eyepieces there, which your favorite eyepieces. So I just wanted to know, what do you use each one of them for? I mean, they seem to be from small to large. I mean, like the aperture, this thing, the But I
Yes,
just wanted to know, what you're using it for, and because I've never heard of the term ortho. What is it? Orthoscopic.
orthoscopic. Okay, excellent.
Yeah.
I'm glad you brought this question up. So the thing is, there's normally when we think of eyepieces, we think of them through their focal length, the millimeters, right? Because that tells you what magnification you will get for a given telescope.
Correct.
But there are many more factors to an eyepiece. The 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 design of the internal design of the eyepiece, the simplest eyepieces has two lenses, but the simple two lens eyepiece will not correct for a lot of problems, lot of image quality problems, right? There are similarly 3 and 4 and 5 lens eyepieces designs that solve some of these other problems. Of all of this, there is a particular design called orthoscopic that a lot of visual observers really like because it produces exceptional contrast. So it's an eyepiece design, orthoscopic. Okay, some of these are brand name designs, like a Teleview Nagler is a specific design that is created by Teleview that provides a certain large field of view and so on and so forth. It has about 6 elements, I think, inside it, 6 lenses. So some of these designs are also brand names, but orthoscopic is a generic design from Germany.
Okay.
Um,
Okay.
so
And
depending on what eyepiece design you have, the parameters like the field of view that you see, the eye relief, how far you hold it from the eye, and what is the contrast, these things will change. And I'm saying that we should use as much contrast as possible.
yes, I got that. That is the best way of viewing, you said. So I understood what you meant. So is it now? I don't have any of these orthoscopic. So should I shift to that for any deep sky objects? You're talking about very,
Depends on,
very deep sky, but I'm talking about just deep sky objects.
correct. Depends on how seriously you want to get into it, right?
Okay.
And what budget you can deal with. If you
Okay.
want an upgrade from the standard Celestron fluorescence,
Mm-hmm.
then the orthoscopics are a very good upgrade.
So
Like
I don't think I'm
multi-coated,
going
you have to
to.
be careful that they are coated. The
They're coated.
multi-coated orthoscopics are a good upgrade.
Okay. Okay. Thank you. Thank you. You answered my
Sure.
questions.
Excellent.
There is
Okay.
one question.
Um,
There is one question, Akash.
yes.
Uh, what is f-stop of an eyepiece?
Yes. Stop of an eyepiece.
Yeah, I don't think there is an f-stop for eyepieces.
Yeah, I've
It
never heard of this concept. There is a notion of a field stop and an aperture stop. Maybe that's what the question is about. The field stop refers to how do I describe this? The field stop refers to the area of the circle that you see when you go into the eyepiece. That's the field stop. The aperture stop is the notion of how big the aperture of the eyepiece is. Maybe they are just referring to the size of the circle you see inside the eyepiece is sometimes called the field stop. That's not to be confused with the notion of f number or f stop in camera. That's a completely different thing, right? That's actually an aperture stop. So,
Okay, the field stop sounds more similar like AFOV.
yes, exactly. The field stop is the AFOV. Although confusingly, the f stop of camera is actually an aperture stop. So these are concepts in optics. You can look them up. I don't want to get into the details of this, but yeah, field stop is the same as AFOV in my understanding.
Sure. Yeah, that's all.
Okay. So some observing notes on galaxies, nebulae, and so on and so forth. Coming up next. By the way, I'm very happy there's a lot of discussion. Please let us continue this after the talk also. I'm learning a lot myself, and I'm sure it's very valuable to everybody. But yeah, let me get into observing galaxies. The first thing I want to mention is the visual size of a galaxy core is usually smaller than what you see in a photograph. And the reason is the eye is a logarithmic sensor. It can differentiate way more shades of gray than a CCD sensor, right? So the visual size of the core of, let's say, M31 is going to be much smaller than the photographic size of the core. And so I'm going to showcase this with a bunch of sketches and pictures and try to explain what this means. So we'll take M31. Here's Dr. Suresh Mohan's picture of M31. So if I looked at this picture, I might say that the core of M31 is this big, right? The brightest part, because all of that seems fairly uniform in the picture. But if I actually look at it from a telescope, chances are this is the size of the core that I will see when I just look into the eyepiece. So I'll see a smaller core. And the reason is that the number of shades of gray that the eye is able to see are much higher than, so what appears completely white in a photograph actually appears gray in the eyepiece. So we can see much more. And one thing that confused me very much when I first looked at M31 is I thought this is M32, by the way, this circle here. When I first looked at it, in the telescope, I thought I was looking at M110. I thought this thing, because of how far away it was from the core, I thought I was looking at M110, because M32, you see, touches the galaxy. M110 does not. This is M110. M110 does not touch the galaxy. So but that's not true, because I mean, in fact, M110 is so faint you can't see it from city skies, whereas M32 is bright enough that you can see it from city skies. So I was looking at M32. What I had fallen for was this, exactly this effect, that the visual core of M31 is going to look much smaller than the photographic core because of this ability to view shades of gray. Then what does it mean? Does it mean all of this detail is completely invisible to us? No, it is visible. You just have to look for it from a dark enough sky. And so when I did that many years later, I started observing in 2006. When I looked at M31 in 2009 with my 17.5-inch telescope, I was able to go all the way to the edge and see this knot, for example, which is a stellar association, and see how my glow goes almost all the way until M32. So if you have to look for it, right? The word I'm going to use for this is that the dynamic range in a photograph is compressed, meaning it can see fewer shades of gray. That's what we call dynamic range. The unfortunate thing is that the sketches also compress the full dynamic range, because when I sketch, I cannot show you all the shades of gray. So if I show you the sketch, you might say, okay, this is what I expect to see. That's not true. Again, the core is going to be much brighter in reality, and these parts are going to be more faint. But we sketch them, like they look in the photograph. We are not able to distinguish all the shades of gray in our sketches as well. So that's something to watch out for. So this is just a flashback. This is what my 17.5-inch back then looked like. I have since sold it, and that was me in 2010 with it. Now let's look at a much more experienced observer's sketch. This is Howard Banish, who many of you recognize as somebody who writes for the Sky and Telescope. He's a very good sketcher. I'm going to show you a lot of his sketches. This is what he saw through an 8-inch. So you see here is M32, and here is M110. And this is the size of Andromeda that we expect to see. But he saw this extra twist that I have never seen before. And it's easy to say, well, where is it on the photograph? Was he hallucinating or something? But if you go to the Deep Sky Forum, there is a thread on this, and there is one more observer who has said, my God, I thought I was the only one who was seeing this twist, and he shared his sketch. That was Uwe Glan. So these are extremely faint features. The thing is, the sketch is not sketched with the same precision, right, of what are the various shades of gray. So you have to be careful again, just like you have to be careful when looking at photographs, you have to be careful when looking at sketches to keep in mind that the shades of gray might not be represented the same way. So yes, if you have a very dark sky, I suspect that that twist is actually this thing here that you see in doctor's sketches. In doctor's photographs. So you can see a lot of detail if you look for it carefully. And but when you first look into the eyepiece, chances are you are only going to see this much, right? So that should be borne in mind. Here's another case study of the same thing. Here's Messier 87, which many of you will recognize as one of the brightest galaxies in Virgo. Big elliptical, the same galaxy where the black hole image was recently produced. So when I first looked at this image, I thought I would see the light extend all the way to these faint galaxies, right? But in reality, this is the size of the core that I saw, and this part was all really faint light that I had. Only when I looked for it that I realized that, M87 extends all the way. So the visual core is going to look smaller. Here's Howard Bannich's sketch of the galaxy. You see how tiny his visual core is. And so he is able to see more dynamic range. But again, sketches don't again capture the exact dynamic range. We compress it even here. This feature here is M87's jet, for what it's worth, which is a challenging visual object. M87 itself is much easier. So that's about observing, just a general sense of observing galaxies. So how do you see details in galaxies? So for details, usually details in galaxies are like H2 regions, which are nebulae essentially, stellar associations, which are like star clusters. So remember to use sufficient power so that the knot is big enough. The knot, by knot we mean one of these two, usually. So these knots normally lie around in the spiral arms of the galaxy, in a spiral galaxy. So first of all, you want to change your power so that the knot is big enough to be observed, not the core of the galaxy, but the knot. Remember, different details at different power. Sometimes if these knots are nebulae, you can use nebulae filters on the galaxy to brighten those knots, right? So those are a list of various popular nebulae filters. And if you can't see all of the spiral arms at first glance, you start connecting up the knots to track the spiral arms. This is something I do in M33. Its spiral arms are not extremely well defined, but if you start seeing the knots and connecting them up, then you will follow that. They will follow that spiral pattern. So that's how I see the spiral arms in some of these galaxies. The easiest of these knots that you can see, even in an 8-inch. If you haven't tried this, please try it. Go look at NGC 604. It's a bright nebula in M33 in Triangulum Galaxy. So I think I have highlighted it. This is Triangulum Galaxy. There is NGC 604. In a small telescope, I know I made this sketch with a big telescope, but in an 8-inch or so, you might be able to see all of these images, all of these features. Remember, this is low power on my large telescope, so you should get these images with higher power on your smaller telescopes. So you can see the spiral arms, and you can see NGC 604. There it is. This is my sketch. This is Howard's sketch. You can see the world of difference. Howard Banich is just really good at sketching. You see, he has spent a lot of hours finding all the nebulae that he can see and marking them on the sketch, and all the spiral arms that he can see. So if you keep trying different powers, look for it carefully, observe more carefully, you can see all of these details. I think this sketch was made with his 28-inch. Here's another case study. This is the Fireworks Galaxy. It is very low surface brightness. Not very, it is low surface brightness. It's first of all challenging to find it, but you can see spiral arms in this if you magnify it well enough in a big telescope. So here I've basically gone through the knots to trace the spiral arms, and I marked on this sketch what spiral arms I was able to see and what I could not see. Again, different magnifications, always worth trying. And I also tried to use filter to see if I can see nebulae pop up. In this case, I don't think it worked very well. Briefly on this topic, Baader makes a filter called UHC-S that has a wider pass band than the traditional UHC filters. So if you're looking for detail on knots where you don't want to kill the host galaxy completely, so you can still see a little bit of the galaxy, UHC-S might be a good filter to consider. I've never actually owned a UHC-S. Okay. One more really faint detail you can see in galaxies, and I really recommend that people with 16-inch telescopes try this, because I'm very curious to see if other people can see these too. These are bridges and tidal tails. Remember in talk 1, I mentioned what these are. Like tidal tails are caused by when two interacting galaxies pull each other, the gravity is stronger on one side, so it leaves like a tail on the other side. To see these things, use extreme averted vision and use sufficient magnification to make the tidal tail thick enough, but don't spread it out too much. And it's very easy to check whether you're seeing it. Go to the eyepiece without knowing what clock position it is at. And when you see it, figure out what clock, check if the clock position you predict matches the field of view. And you can also check the length, how far you think it goes. For bridges, you can hardly see it clearly if it's a spread out bridge, right? You scan the field and you see that there's a slight increase in brightness of the background. So you go back and forth perpendicular to the bridge with your eyes and see if you can see an increase in the brightness. And that's how you can tell whether you are seeing a bridge between two galaxies and so on and so forth. This is the same technique you use to observe low surface brightness nebulae. You try to map out the transition from dark background to brighter background. And you won't like see it like a clump. Some of these things you have to like look for them carefully, as I just described. This is the brightest tidal tail that I know of, which I have seen multiple times with my 18-inch. Good tidal tails that are visible in 18, 16-inch apertures are hard to find, but this is one of them. This is not difficult in my 18-inch. So I'm pretty sure it will be visible in 16-inch from good conditions. Here's, however, a sketch of it through a 48-inch. So there you can see I'm even mapping out this faint other tidal tail, like the backward tidal tail. This part, of course, I cannot see in my telescope. This part I can. So it's obvious on a 48-inch telescope. So I encourage you to try this, the mice galaxies. The other tidal tail I managed to see in my 18-inch is this galaxy. Some people call this the bird head galaxy because it kind of looks like a bird with a bird's head with a beak. It's an interacting pair in Lyra. And again, this starburst here in this tidal tail, this I was able to see in my 18-inch. There are maybe like 4 or 5 good tidal tails. I still haven't explored all of the ones that are visible in an 18-inch, but it's not something that's out of the league of 16-inch, 18-inch telescopes. This is with my 18-inch. Of course, I've seen this in the 48-inch. It's just like looking at a photograph. I think this is one of the deepest observations in my 18 so far. This galaxy here is 17th magnitude. And I might have seen 1 or 2 pops of it, which really is one of the faintest things I've seen in my 18-inch. Okay, so I guess the moral of the story there is don't be afraid of tidal tails. Give it a try with the right technique. You might be able to see it. Before I pause, let me breeze through nebulae. Firstly, you would have all heard that there are photographic nebulae, like nebulae like Horsehead are very easy to photograph, but extremely difficult to observe. The reason this is, some of you already know this, pardon me if I'm just repeating for those of you who know this. the strongest emission of hydrogen is in the visible spectrum is actually in red, is the H alpha line. In a typical nebula, the H beta line, which is in the green blue region, is about 2 to 3 times fainter. Unfortunately, the eyes scotopic response, which we discussed in the first, the night vision response, is basically very poor in red. It doesn't see red very well. So when you look at a nebula, you are actually seeing this green-blue emission from what we call H beta from hydrogen, and also the oxygen emissions, which are much fainter. But that's what you can see more easily. Like I said, they are about 2 to 3 times fainter. This is why nebulae like Horsehead are actually challenging. But that's not the end of the story. The other reason that they are challenging is that they are very low surface brightness. And to observe low surface brightness objects, you have to stay with it and apply all the techniques that we can think of to discern that low contrast. CCD will capture it very easily, but for our eyes, you can still see Horsehead Nebula. It's even in a 4-inch telescope, I'm told, but it takes effort. Okay, here's a spectrum of Eta Carina Nebula that shows you see how much stronger the H alpha emission is compared to H beta and O3. But this is what we can see. We can't see the H alpha very well. There are, of course, it's not that you are completely blind to H alpha. There are objects where you can see the pink, but usually it's from your cone, not so much from the rods. So that's why nebulae are hard. And what nebula filters do is they don't boost the nebula signal. They suppress the background. And as we have said, contrast is what is important. And the nebula filter basically makes the entire background so dark that the tremendous increase in signal to noise ratio allows you to see very faint nebulosity. Here's the spectrum of a Lumicon UHC filter. Lumicon is one of the good brands for filters. UHC stands for ultra high contrast, for those of you who don't know about it. These will allow only those emissions from hydrogen and oxygen to get through and suppress all the other sky backgrounds, so you see the nebula very clearly. I mean, it still takes effort to see it, but it gives you tremendous boost in signal to noise. Here's a good example. This nebula, which is Abel 7, this is a planetary nebula. You can see it is pretty much averted vision on the DSS plate. For an 18-inch, seeing something like this, if it were a galaxy, forget it. I mean, I wouldn't even, I would try it because we are all crazy like that, but it's extremely hard. But because this is a nebula and it's emitting strongly in O3 and H beta, it's not tough at all. I mean, it is tough, but it's not extremely hard like the DSS plate would make you imagine. So here's my sketch of it, and the amount of detail I've been able to see is all thanks to this filter, right? Like I've been able to say that this part has a darker portion, and these are the brighter portions, and all of that. And the one thing that should be noted is when you put in a nebula filter, what is the brightest part of the photograph does not necessarily match what is the brightest part on your eye, because you're looking at the maximum H beta emission, whereas the photograph is trying to get the combined light, right, from all the spectral, from all the gases in there, all the spectral lines. So, whatever your sensation is in the eyepiece is going to be different from the photograph, but you can see all of these details. Filters help tremendously. Now, coming to very large nebulae are some of the toughest objects, extremely low surface brightness. This object that I've shown here is, I think it's the largest planetary nebula known. It has the size of 1.6 degrees, which means basically it is three full moons in 3 full moon diameters in size, and so it's extremely large and diffuse, and it's a challenge target for even photographers. But if you try, you can see a little bit of it. And here the technique is to scan across this brightest boundary, star hop to this region, scan across this brightest part of the nebula, and see if you can detect a change in background contrast. That's the best you can do for these. So for these, a photograph is extremely helpful. Here's my observation of this nebula. So I started at some point. Here's a reference star field, and I've scanned it, and the glow kind of switched on in that region, as you can see my log. And that's how I've been able to tell that this is the rough boundary of the nebula. And as you can see here again, I see a difference between the UHC nebulosity and the O3 nebulosity. And that's not surprising. For many of these big planetary nebulae, the O3 region is actually offset from the H beta region. And Rainer Vogel on his website, I have a link to it in the presentation. He has a very good explanation of why this happens. It has to do with the dynamics of the star and the interstellar medium and the nebulosity. So the view in UHC and O3 can be different. I've already said all of this while I just described, and there's Rainer Vogel's website, which is he has a very good list of large planetary nebulae. I think he might be the best reference for big planetary nebulae. Again, like I said, this means that sky survey images are not a good reference. You want to try to find narrow band images from amateurs. One more note on reflection nebulae. Sometimes it's very hard to tell whether you're seeing a reflection nebula or some halo because of bad transparency and bad optics. My favorite example of this is NGC 2023, which lies just below the Horsehead. If you look at it and you didn't know it was a nebula, you would have said, oh my God, the transparency of the sky today is really bad. But the funny thing is, you go look at the other stars, they're all fine. Why is only this star, has a halo around it? The answer is because it's a reflection nebula. So it's very hard to sometimes see reflection nebulae. But once you get a hang of it, ask yourself, like, if I see other stars, am I going to see the same halo around it? If you don't see them, then clearly it's a reflection nebula. The other way to see is decide whether it's a halo from bad transparency or whether it's a reflection nebula. Is you see if it's an asymmetric shape, and as you pan the field, the shape doesn't change. Then it's not coma or something like that in your eyepiece. Sometimes you need to move the bright star out so that you can see the reflection nebula. That when I was preparing this slide, I just remembered that there is this crazy object called Barnard's Merope Nebula, not to be confused with regular Merope Nebula. This is Barnard's Merope Nebula, and it is just like a faint extension from this really bright naked eye star. So here's the faint extension, and Howard Banich. This is again Howard Banich's sketch. And Howard's tip here is to time it such that the nebula is between the diffraction spikes of the telescope vanes, like the spider vanes. So you may have to go to extreme lengths in to try to detect some of these faint and confusing reflection nebulae. But again, it takes more. What it takes is mostly dark skies and patience and good observing skills. Don't let anyone tell you that these photographic nebulae are impossible, because here's a sketch by Howard Banich in an 8-inch telescope of all the nebulosity surrounding Pleiades. Extremely detailed sketch. Now, one should note that Howard is blessed with a really good sky. His part of the country has some really, really good skies. So not everyone might have the same fortune, but I have seen some of these nebulae myself from bottle 2 kind of skies. You don't need bottle 1. I think you can get away with bottle 3 also. Like I said, almost all of the quote-unquote photographic nebulae that you just cannot see have all been seen visually. These are my logs. As you can see, some names: Witchhead Nebula, Flaming Star Nebula, Soul Nebula, Elephant Trunk Nebula, Heart Nebula, Cone Nebula. They're all here. Merope Nebula, from Pleiades, and so just good technique and patience and dark skies. I think dark skies are very important, and filters help a really big long way. And finally, as we end, I think I will stop after this. Here's a sketch, this and the next slide. Here's a sketch of Cone Nebula by Mel Bartels. I mean, I'm amazed at the amount of detail he has captured. Remember, this is the brightness here is not to scale. We compress the dynamic range while sketching, like I've said. So this nebulosity is extremely faint, and it takes a lot of effort to discern all of these faint nebulosity, but it's possible. Cone Nebula is one of the really hard objects. The Christmas tree cluster, which is next to it, is super easy. See it in the 8-inch telescope very happily, but Cone Nebula, you need really dark skies. And Mel Bartels is an expert on observing these really faint nebulosities. In fact, even the integrated flux nebula, if for those of you who know what that is, it's or for those of you who don't know what it is, it's these are very faint nebulosities that are far away in the halo of the Milky Way galaxy that are illuminated by the collective light of the Milky Way stars. So that's why they call them integrated flux nebulae. These nebulae are challenging targets for astrophotography, but they are also possible to be seen visually. It's with the right technique, with the right kind of sky conditions. I know many imagers won't believe that it is even possible, but here, these are very experienced observers, and I'm sure that they are not, that you can trust that they are seeing it. And multiple observers will corroborate on these things. And many people have seen IFN. It's not just Mel Bartels, but he's the one who has pushed it the most. Mel Bartels seems to say that a very wide field, like the richest field telescopes, you see his F number here is f2.7. He says that the very fast telescopes now very fast telescopes are hard to buy in good quality. Mel Bartels is also, as you know, an exceptional telescope maker, so he makes them himself. He has that luxury. So he says that these very fast telescopes are exceptional for these very low surface brightness nebulosities. And he has an excellent article in Sky and Telescope in April 2017, where he has charted out a lot of the IFN that you can see. It's called Herschel's Coast. So on that note, don't let people discourage you about observing nebulosities. But I will tell you they are really hard. They need excellent skies. Typical low surface brightness objects, if the sky quality is not good enough, you won't see them as well. It's not like a high surface brightness object where you can throw aperture and power at it in any sky. I mean, not in a city sky, but like in any average sky. These are really hard, but they can be done. Okay, so I will end there, and maybe we'll pick it up. There's very little left in observing, as far as I'm concerned. We'll pick it up next time. So I am available for a few more minutes, I guess, so we can have any discussion as long as people want to discuss. I'm happy to discuss.
If there are any questions, people can unmute themselves and ask, please.
Sir, this is Sukumar. Why there are filters for few elements only, like sulfur, O3, and hydrogen alpha, like that? Is there any reason?
These are the elements that are normally found in these gas clouds, right? These gas clouds are very low density areas, and as you know, hydrogen and helium are so abundant in the sky that all the other heavy elements are very rare. So typically, if you see any cloud in the night sky, chances are it's made up of hydrogen and helium and a little bit of these other simple elements. The simple answer is because all the other heavier elements are hard to produce except in a supernova, right? You can't produce very heavy elements in stars through nuclear fusion. You need a supernova. So that's why only the simple and light elements are typically found in these gas clouds. At least that's my understanding.
What about sulfur, sir? Oh, I understand with your answer that hydrogen, helium, oxygen are very gaseous, very basic elements. But what about that sulfur that I added?
Again, I am not an expert, but I assume that sulfur is light enough to produce in a star, right? But for example, iron is very hard. Is the last element that is produced in a star, if I remember correctly. So that's just my understanding. I don't really know much more than this. I'm sorry.
Okay, thank you, sir.
In visual observing, we primarily focus on H beta, hydrogen emissions, and oxygen emissions because that is what is most common in nebula. In nebulae, I guess the sulfur emissions are probably fainter or probably in the red, and therefore we don't care about them. I haven't figured out why we don't care about sulfur and nitrogen, but normally in visual observing, it's all about hydrogen and oxygen.
Sulfur is an infrared, right? It's beyond
Oh,
red.
is it? Okay, I see.
If
Okay,
I
that
remember
explains it.
correctly.
One more
I guess
question,
that
sir.
explains it.
In,
Yeah.
in helium also, I think, take part in nebulosity, I think so. Why there is no helium filter like that?
I think
My
because
question
of I think you're right that helium is also very abundant in nebulae, but I think all the helium emissions are in the red part of the spectrum, so they are not good for visual observing, and that's I think why we don't use helium filters.
Okay. Thank you, sir.
Also, is it because helium maybe doesn't have any free electrons and it's
Doesn't
probably
emit as
not,
strongly? I think you're
I,
right. Also right. Uh,
yeah.
yeah, I'm not sure because the atomic transitions that determine how bright a line is also also depend on these things like how many electrons there are in the shell. I think you might be right, Kirti. You might not see
Okay.
a lot of emission even though the helium is abundant because it's hard to ionize.
Okay.
I have a question about observing dark nebulae.
Yes.
So, do UHC filters help when you're observing dark nebulae? Do they highlight?
No.
Do they highlight it in any way? Okay.
Okay, depends. Right. So of course, dark nebulae have no emissions of their own.
Right.
These UHC filters and so on
Can they
are
highlight the
helpful
boundaries
only.
of dark nebulae? Supposing there
Yes,
is.
absolutely. If
Yeah.
if your dark nebula is inside a NH2 region, like it is inside a emission level nebula, like for example the pillars of creation or Bok globules and elephant trunk nebula, things like this, I'm sure UHC will help because it boosts the contrast of that boundary also.
Okay.
Right. Whereas for dark nebulae like the coal sack or things like that are not part of an emission nebula, then it doesn't make any sense to put a UHC filter on it. For example, on the coal sack, you don't expect to get anything from it.
Okay. So in most cases, when you're looking at the background of the sky, you just look for a dip in the brightness. When you're observing.
Right.
When you're looking through the eyepiece and there is a certain level of background glow, right? You have the sky. It can be dark or darker. So if you find something that is darker than the glow in the eyepiece itself, that there is a possibility that is a dark nebula.
Absolutely correct. So sometimes sometimes you might be looking at a reflection nebula that is really large. And there is a dark feature inside that reflection nebula. So the reflection nebula could fill your entire eyepiece, and then you see these dark patches in that reflection nebula. That's entirely possible.
Okay. Okay.
Akash, I have a very silly question, but it's
There's
just
no silly
out of
questions,
curiosity.
Leela. Yes,
Yeah, see, when you showed the drawings, I wanted to know whether
yes.
they start with black paper and then use white pencil.
Good question. Almost everyone that I know sketches on white paper with a dark pencil, and then they invert it on the computer after they scan it. They do the color inversion on a computer. So their sketches are on white paper with black pencil usually.
Thanks, Akash.
Yeah, yeah. So I hope some of you who have not seen like galaxies yet, who are still seeing open clusters and globular clusters, I encourage you to go try pointing to Andromeda galaxy and so on, and seeing if you can um, make these distinctions. Like where is M32, where is M31, and both M31 and M32 you should be able to see from the city. So I encourage you to try this.
So I just checked this sulfur 2 line. It's at 672 nanometer.
That is far in the red. Yeah, close to infrared almost. So yes, definitely not good for visual observing.
Right, right. So I think somebody in the chat asked why there are no carbon lines or something like that. I logged out, so I lost the question. But there was some question like that. I
Is
think
it carbon monoxide lines? I think molecular emissions normally are very faint, and usually molecules are what you see in dark nebulae, right? So it's very hard to visually see those things. So I don't think we use filters for carbon dioxide. I don't know about carbon itself. Uh, I really don't know. Like I said, first of all, the gas has to be abundant. It has to be easily ionizable, and ionizations have to be within the range of nighttime visual observing, which is mostly blue and green. And it looks like it's mostly oxygen and hydrogen that fit this criteria.
Mm-hmm. Yep.
Just
So are
one
you
more
also?
question. Sorry.
Go ahead, Leela, ma'am. Sorry.
Yeah. See, I've never used it, but I have oxygen filters. I've never used it.
Yes.
Even to see and like any nebula that is visible now, if I use it, it'll make any difference. I mean, I've got
Oh
only an
yes,
8 inch.
tremendous improvement. You should see.
Okay.
You will see tremendous improvement. Uh, you have to keep in mind that you will get different views with the filter and without the filter, because it will. In your case, the oxygen-free filter will cut out the hydrogen emissions also somewhat,
Uh-huh.
so you won't
Yeah,
see
it's
the
oxygen
hydrogen
free. Yeah.
emitting part of the thing.
Uh-huh.
So, for example, people say that Crab Nebula looks very different unfiltered
Huh.
versus with an oxygen-free filter. But
Uh-huh.
if you're just trying to look at the object, oh my God, you will see a tremendous difference. I encourage you to try it.
Okay. Thank you so much. Thanks.
Yeah, the only places where these filters won't work are dark nebulae, reflection nebulae, and protoplanetary nebulae. They work very well for planetary nebulae and ionized emission nebulae like Orion Nebula or Swan Nebula, and so on and so forth.
Uh, yeah. Okay. Great. Because I've never used it. I've just got those O3 filters and I've just never used it. Thank you.
Sure.
Also, Akash, probably for comets, this O3 filter might be good, right?
Oh, I don't know about that. I know for comets there's a separate filter called a Swan band filter. Uh, Comets, maybe, I am not sure.
Yeah, you're right. Sorry, I got confused. It's the Swan band filter.
There's a different filter for comets that looks at more, I think, molecular emission lines or molecular emission bands rather. So it's a broadband filter, if I remember right.
Okay.
I would like to share a observation.
Yeah, absolutely.
Whenever you put on a filter like oxygen or even light pollution reduction filter, suddenly you see that the view in the eyepiece has darkened considerably.
Yes,
And
absolutely.
what I feel is it's like going into a movie hall when the movie is on. Suddenly, you have to adapt your eyes even more. Uh,
Oh yeah.
what I mean to what I mean to say is that it takes some time because you are watching in your eyepiece and the view is bright, and suddenly you put on the filter and the view becomes dark. You have to adapt your eyes. And there is one more observation about these filters, that they work exceptionally good on larger telescopes. If you're using a filter on a small telescope like 6 inch, uh, it won't have much effect. That's my
I
observational
see.
experience. Yeah.
Interesting. I have also heard this from other people that filters work very well in larger telescopes.
Okay, so I'll try it on the 8 inch and let me see.
Yeah. That was Ajay, right? I think Ajay, in fact, in the first talk, uh, I was showing this plot of the dark adaptation versus time in the human eye. And the interesting thing is it stretches below 21.8, which is the standard sky brightness, like the darkest sky that you can think about, 21.8 magnitudes per square arc second. So it means that even the night sky is kind of preventing you from dark adapting. So I completely agree. I think putting a nebula filter will you have to allow for yourself to dark adapt to the black background to see the really faint objects.
Yes, this is Ajay, and I want to reiterate that as soon as you put the filter on, you get disoriented because
Yes,
previously you were
definitely.
able to see some
Yeah.
stars, and so have to give it time, maybe 30 seconds of observing, continuous observing, and then your eyes start to adapt, and then you see the effect of the filter. So you need to give it time. You don't put the filter and see nothing and then you remove the filter immediately. Don't be so quick and hasty.
Thank you.
That's a very good
That's
point.
useful.
Thank you, Ajay.
Also,
Yeah,
also
thank
you
you
have
for that.
to also you have to put the filter after you find the object. With the filter, you will not be able to find the
Yeah,
object probably.
yeah, I agree with that. The I think one of the biggest challenges is if you don't have tracking and you're using a filter, try to get the object back is going to be a nightmare because you won't see any of the reference stars. So yeah, you have to try to find the object exactly, know which way things are drifting, and then put the filter as quickly as possible. So many people use filter wheels, or rather, not filter wheels, filter slides. I don't have a filter slide. I put my filters manually, but then I have tracking, so it's not such a pain.
Also, what I have found is when you use filters, when you put the filter, you have to again refocus. I don't know whether it's because I mean it's inherently like that, or whether it's because we are changing the focus when we take the eyepiece out. But every time you put the filter in, it's defocused, and you have to focus it again.
I think you're right because the filter adds light path, right? It has a different index of refraction, so it'll shift the light path a little bit.
Oh, there's quite a bit
Mm,
to it.
yeah.
Thanks a lot.
Yeah, the point that Ajay made about getting disoriented and allowing for 30 seconds to adapt to the filter, I completely agree with that. It's a very good point.
Thanks.
Any other observations, comments? Has if any one of you have seen some of these very faint nebulae, I'm very curious to learn what aperture, what sky conditions, and so on. So I encourage you to share this.
Okay, I think we can end the session here and
Yeah.
continue the discussion on the WhatsApp group or in the next session. So thanks, Akarsh, for the wonderful presentation again.
Thank you everyone for the discussion. I really enjoyed all your comments and especially the inputs on the orthoscopics and so on and so forth. So thank you very much.
Yeah, same here. It was great. It was a great session as always.
Okay.
Yeah.
Yeah. Actually, let us end. I want to ask everyone on WhatsApp and other media on how interested you are in like part 4, which is mostly about stories and about an intro to various observers who have done amazing things like Howard Banach and Jimmy Lowry and all of these people. So if there is no interest in that, I would rather skip it. But if there's interest, I can tell stories. So it's more story-ish. So we'll discuss on WhatsApp to see if there's interest in that. Okay,
All
thank
right.
you.
Thank you, Akash. Bye bye.
Thank
Good
you.
night.
Akash.
Bye.
Thank you, Akash. Bye.